Now, welcome back to Lecture 4. In this last segment, we are going to provide one more example of equational reasoning that we use to prove a logical equivalence. So let's go back to an example that we are quite familiar with, namely the two propositions S1 and S2 that constitute an argument that we discussed a couple times before. Now, in this segment, the question we're trying to answer is whether S1 and S2 are logically equivalent or not. So let's think about how to solve this problem. Well, we already solved it, and we know the answer is yes. We did that in Lecture 3. And the method we used there was to use the truth table algorithm. Remember, we built a truth table with both S1 and S2, and then we checked that the two columns corresponding to the input propositions S1 and S2 were identical. So we already proved that these two propositions are equivalent. Feel free to do it again if you need more practice with that algorithm. But what is more relevant here is to provide a second proof of this logical equivalence using equational reasoning. Now remember that equational reasoning is a useful approach when you're trying to prove that two propositions are logically equivalent. The way it works is you start with one of those propositions and you repeatedly replace components of it using known logical equivalences until you end up with the other proposition. The one you are trying to prove is equivalent to the first one. Now notice how in this second approach, I don't call this ER approach an algorithm. And the reason is that I have never specified in detail or at all not only the steps that I'm supposed to perform, meaning which substitutions to perform, and even less so the order in which they should be performed. So this approach, as stated so far, is really not an algorithm. There's a lot of art involved here. There's a lot of ingenuity where you have to choose at every step what's the best way to go. So that's why you need practice with this. And so let's do it together. So what is the first step? The first step is to start with one of the two logical propositions. Sometimes it's easier to start from one than the other. But if you don't know any better, like in this case, you just start with the first one. So I'm going to write down the first proposition, C or E implies not P, which is nothing more, nothing less than S1. Okay, so the first step wasn't too bad. We just randomly picked S1 as the starting point. Now the second step is actually crucial to not only whether you will succeed in completing this proof, but also how neat and elegant and short your proof is going to be. So my advice here, if you don't know where to go from here, is to think about the ultimate goal of your proof. Where are you trying to get? You're trying to get to this proposition right here, namely S2. So in order to decide what the first substitution should be, it would be a good idea to actually compare where you currently are, S1, to where you want to be, and determine first the commonalities between those two propositions and then their differences. Hopefully the differences will indicate or give you an idea of which transformations or substitutions you need to perform. So let's look at S1 and S2. What do they have in common? Well, first of all, they use the same atomic propositions C, E, and P. Not much we can do about that. That's a good thing since we want to show they're equivalent. But the more important observation is that both S1 and S2 are conditionals. That's the first crucial observation. And the second one is that the premise of S2 is the negation of the conclusion of S1. So maybe that should ring a bell. What is a substitution that allows you to preserve conditionals, go from one conditional to the other, that also allows you to switch the order of the premise and the condition. In other words, the P here would end up on the other side of the arrow. And not only that, but the premise of one is the negation of the conclusion of the other. Do you see it? That's right, that's contraposition. So, after this hard analysis, but really crucial because now we're almost home, assuming we didn't make a mistake, let's apply this second step by starting from S1 and using the contraposition logical equivalence. And when we do that, what do we get? Well, we get the negation of where we started from as the premise of the conditional, that is not P, and then the conclusion of the new conditional here is also the negation of the premise that we started with. And again, don't forget to justify every step in your equational reasoning with a justification for every substitution. Alright, so we should feel pretty satisfied that we discovered and performed a step that looks very useful. It looks useful because notice we're trying to get here. And we're not that far. We already have the conditional. We already have P on the left-hand side in both propositions. And we have C and E on the right-hand side in both propositions as well. So what should we do next? Well, another hint that applies almost all the time is to get rid of the double negation. Now, it's not always a good idea. There are some rare cases where you don't want to get rid of this double negation here because you might need one or two of those in a later step, a substitution step. But in this case, it's unlikely to be true because notice we're trying to end up with a P on the left-hand side. So clearly, if we apply double negation here, that will give us P directly in one step. So let's choose that step and let's execute it. Again, don't forget to justify every step in your equational reasoning. So this new equality is justified by the double negation law. Alright, so this third step looks quite promising. I strongly encourage you to double check every step. Here it looks like I did not make a mistake in applying the double negation law, so I'm just going to keep going. But I'm stuck. So what is my standard hint here? Well, compare where you are currently in your reasoning to where you want to be. And what you notice is you're really darn close. First of all, you want to have a conditional whose premise is P, and we already have a conditional whose premise is P. So really the only sub-proposition that we need to focus on is this one. We need to convert this negation of a disjunction into a conjunction of negations. The propositions are the same. Now, does that ring a bell? Exactly. You can do that in one step. That's called De Morgan's law. Now, which one is it? Is it the first one or the second one? You got it. It's the second one, where the negation of a disjunction can be replaced with the conjunction of the negations. Don't forget to double check your substitution. Don't forget to justify every step. This one is all right. And now we realize we're done. We just obtained S2. So let me indicate that right here. And so what we just proved is that by starting from S1, using equational reasoning, one substitution of equals by equals at a time, we end up with S2. Therefore, we can conclude that S1 is indeed logically equivalent to S2. And that was the goal of this exercise. So congratulations, and this wraps up the last segment of Lecture 4.